Alright, section 3.3 is the differentiation rules. We're going to like this section because it gets us away from all the limit definition stuff. The first rule we have is the derivative of a constant function. Remember, a constant function is a function that's just a straight horizontal line. So, if f has a constant value, f of x equals a constant, then the derivative is going to be equal to 0. Because remember how we found the derivative here? It's the slope of the tangent line. If you have a constant function, guess where the tangent line is? It's just that line. And the slope of a horizontal line, we said, is 0. The next rule we look at is called the general power rule. It says if n is any real number, then the derivative with respect to x of x to the n is n, meaning bring the power down front, times x raised to the n minus 1. Subtract 1 from the power. Okay, this works as long as n is any real number. Doesn't have to be an integer. For example here, suppose I asked you to find the derivative with respect to x of x to the third. Using this general power rule, we would bring that exponent down front, which is the 3, and then this would be x raised to what power? Squared. No limits, no h's going to 0, no foiling or cubing or anything. It's just a rule. Aren't you glad we did this? Because now I'm telling you, you can use these rules instead of all those limit definitions in the previous sections for finding equations of tangent lines and all that stuff. Isn't that nice? Differentiate the following. All right. So for example 1, typically when you have functions, a is going to be easy to differentiate using the power rule. B and C we need to rewrite. So I'm going to have a column here that I call rewrite. Then we're going to differentiate using the power rule, and we will simplify if need be. So on A, there's no need to rewrite this. It's just f of x equals x to the 5th. When I take the derivative using the power rule, I get f prime of x is equal to what? 5x to the 4th, and there's no reason to simplify it. It's already done. G of x, when I rewrite this, remember when you have a radical there, you rewrite this as a rational exponent. This is going to be x to the 3/4 power. Do y'all remember that rule? Let me remind you. If you have the nth root of a to the m, that's equivalent to a to the m over n. The numerator is the power, the denominator is the root on a rational exponent. So when it's written like this, when g is written like this, it's easy to tell what the derivative is going to be. G prime of x is equal to what? 3/4 x to the negative 1/4. Now, we don't want to keep negative exponents either. So g prime of x is going to be rewritten as 3 over 4x to the 1/4, or you could write the 4th root. I don't have a preference one way or the other. Typically, the rational exponents are what I'm going to go with. Yes, sir?
Can you explain how you use the power rule again? Because I'm not getting how you...
Okay. What I do with the power rule, let me go back up here to the definition. If you look right here, it says whenever you take the derivative of x to the n, it's going to be n times, which means that this exponent right here is going down front. And then you subtract 1 from the exponent. Your new exponent is going to be the original exponent minus 1.
All right.
Okay? So right here, 3/4 was the original power, so I moved it down in front. That gave me the 3/4 here. And then 3/4 minus 1 is negative 1/4. And then we're using the rule for negative exponents. Do you remember that rule? It says if a is raised to a negative 1, then that's equal to 1 over, let's say a negative n, then that's equal to 1 over a to the n. Just reviewing properties of exponents that you've seen before, but you've slept since then. The last one here in example 1 is going to be h of x. I want to use the negative exponents now to rewrite this as x raised to the negative 4. Do you see why? Because now I can use my power rule. What you cannot do is just take the derivative with that in the denominator and use the power rule. You need to rewrite this so that you're looking at h prime of x is equal to negative 4x to the negative 5. When we rewrite this, h prime of x is going to be equal to negative 4 over x to the 5th. Do you see why I said you can't just take the derivative using the power rule with this down here? It's not the same thing. It doesn't work. What if we have a constant times a function of x? Well, this constant multiple rule says that if that's the case, then the derivative is just going to be that constant times the derivative. Let's do our columns again where we're going to rewrite, use the power rule, or let's just call it derivative now, and then simplify. All right, for A, we're going to rewrite this as f of x equals 3x to the negative 2. When we take the derivative, we get f prime of x is equal to 3 times negative 2x to the negative 3. So now we're going to simplify this. We don't want to leave it like this, so we end up with f prime of x is equal to negative 6 over x to the 3rd. All right, g of x. Rewrite the function. G of x is equal to 5/3 x to the negative 2/5. When I take the derivative, we get g prime of x is equal to 5/3. By the way, do you see why that 3 stayed in the denominator? It's a constant. It's not a function of x. I don't need negative exponents to move it. It can stay there. So that's 5/3 times negative 2/5 times x to the negative 7/5, I believe. Is that right? Yeah. So we can simplify this, and we're going to get g prime of x is equal to what? Negative 2 over 3x to the 7/5. See, these 5's right here are going to cancel out. H of x. When I rewrite this, what am I going to write? 6x squared over 7 is the same thing as 6/7 x squared. It's just easier to take the derivative when you write it like that. So we end up with 6/7 times 2, and because I'm multiplying it by a fraction, I'm going to put that 2 over 1, x to the 1st. There's no need to write the exponent when the exponent is 1, so h prime of x, when we clean this up, is going to be 12x over 7, or you could write 12/7 x. It's the same thing. Okay, y, rewriting this, is equal to what? When I take the derivative, y prime is times, that's over 1, x to the, so y prime is going to be negative 3/2, or let's do this, negative 3 over 2x to the 1/2, or 2 square roots of x, whatever makes you happy. All right, y is equal to what? Y prime is equal to negative 7/3 times, and anything raised to a power of 0 is? Very good. So that's 1 times 1 is 1 times negative 7/3. The derivative is, this is one worth remembering. If you just have a constant times x, the derivative of just an x without a power is just that constant. The sum rule for derivatives. Basically, you can distribute derivatives across addition and subtraction. So we want to find the first and second derivatives in example 3. Well, the first derivative is what we've been doing. Guess what the second derivative is? It's the derivative of the derivative. So if this is y, what is the first derivative? 12x minus 12, negative 3, subtracting from a negative. You add the number, keep the sign. So there's the first derivative. The notation for the second derivative, not real hard, it's just 2 hash marks. Now that's if you're using this notation. It's a little more complicated if you're using this notation, dy dx. That's the first derivative. The second derivative would be the change in y for the second time with respect to x for the second time. It's d squared y over dx squared. That's why I like the primes, by the way. Prime, double prime. Triple prime. Okay, so the second derivative now. The derivative of 12x is The derivative of a constant is 0. 0 is not nothing. And then the derivative of the last term is, very good. You found the first and second derivatives. I didn't tell you to simplify, so hey, let it be. I'm using this rule, but there's a constant there. But notice on these problems, whenever we have a constant in front, we ended up multiplying that original power times the constant that's in front. I'm cutting out this middle step and just going straight to the end here. So 2 times 6 is 12. Negative 2 times negative 5 is positive 10. This says that if you have the derivative of a sum or difference of terms, you can take the derivative of each term individually and add the derivatives together. This just means that you can distribute derivatives across addition and subtraction, just like you can limits, and derivatives really in the background are limits. Good questions. All right, example 4. Find dy dx if y is equal to this. Ooh, I guess I better go over the derivative with respect to x of e to the x. The derivative with respect to x of e to the x is e to the x. Okay, that was easy. Okay, so now we're going to find dy dx. So I'm going to use the dy dx notation is equal to, there's a constant times a function of x. So this is going to be 3 e to the x, because the derivative of e to the x is e to the x, plus there's a constant, so we bring it down and subtract 1 from the exponent. E, remember, is a number just like pi is a number. That's a E. 2.718281728. Pi 3.14, don't need any more. Example 5. Find the derivatives of all orders of the following function. That means we just got to keep going with the derivatives as far as we can. Wait a minute. We're multiplying two functions together. We have rules for adding two functions, the derivatives of functions, but not for multiplying. We don't have a rule for that yet, so we're going to have to multiply this out and then take the derivative. You've got to simplify. So right now, we have to multiply first. So that means we got to distribute. So we're going to rewrite this as y is equal to x cubed plus 6x squared minus 6x minus 2x squared minus 12x plus 12. Combining like terms, we get, there's the x squared, there's the x's. So we end up with y equals x cubed plus 4x squared minus 18x plus 12. There's our function. Now, the first derivative is going to be y prime. Y prime is equal to what? 3x squared plus minus second derivative, third derivative, fourth derivative, y, and then we don't use tick marks, we put in parentheses a little bitty superscript 4. So we know that it's not a power, we put it in parentheses, and that's going to be 0. So we've taken all of the derivatives we can, because from here on out we just keep getting zeros. By the way, whatever the highest power of x is, you can take that many derivatives. Now we're going to look at, because we don't like multiplying all this stuff out all the time, we're going to look at how to take the derivative of a product. U and V are both differentiable functions of x. You need to know that. So here's a function of x times a function of x. We'll look at this problem. Here's a function of x times a function of x, right? The way this works is you write down the first function and then you multiply by the derivative of the second function. So this is first function times the derivative of the second plus the second function times the derivative of the first. First times the derivative of the second plus second times the derivative of the first. You will memorize this. It's not even a suggestion, it is a command. You will memorize this. Or you will fail, because we use this a lot. So in example 6, we want to find the derivative, but we don't want to distribute. So we're going to use the product rule. First of all, identify what your first function is and your second function. Now, dy dx, according to the product rule, is going to be the first function times the derivative of the second function, plus the second function times the derivative of the first. And I think I'm going to let this stand for now. I just wanted to see if you could follow the pattern for the product rule. I'm not going to make you simplify it out right now. when I took the derivative of this term right here. The derivative of a constant is 0, so I don't need to write it down because 0 plus the derivative of this is just going to be the derivative of that. And using the power rule, you bring that power down times the 2 in front. 5 times 2 is 10, and then we subtract 1 from this power, and that's where the x to the 4th came from. Just to check this one using the product rule, we're going to come back up here. Let's try the derivative now using the product rule. Using the product rule, we get y prime is equal to the first times the derivative of the second plus the second times the derivative of the first. I could FOIL this out, and that would give me 2x squared. First outside gives me plus 6x minus 4x is plus 2x. Last gives me minus 12 plus x squared plus 6x minus 6. Cleaning this up and combining like terms is 3x squared plus 8x minus 18. Well, what do you know? It's the same thing we had over there. I just wanted to prove to you the product rule works. So you're convinced. That's all I needed you to be, was convinced. All right, the derivative using the quotient rule. Now I have a cute little way to remember the quotient rule as well. Here, once again, u and v are differentiable functions of x. What I call this is low for the bottom, high for the top. When you hear the word d, it means take the derivative. So this is low d high minus high d low all over denominator squared. Low d high minus high d low all over the denominator squared. It's corny, but it'll help you remember it. Remember it. I don't care how you remember it. Feel free to use my low d high minus high d low. Somebody else came up with it, not me. So let's find the derivative now. So we're looking at z prime is going to be equal to low d high, tell me what to write, minus high d low all over the denominator squared. And yes, you do want to clean this up because of what's coming. You need to practice cleaning up your algebra. So let's continue simplifying this. So this means I need to distribute this negative 3 here, and I need to FOIL this out and then distribute that negative. So this is going to give us negative 9x squared minus 3x minus, and then this is going to be 4 times 6x is first outside, inside, and last all over the denominator squared. So now I want to come along and distribute this negative to these terms, and I can go ahead and combine like terms as well. So this is going to give us z prime is equal to negative 9x squared minus 3x minus, let's see, I have like terms in here. 24 minus 3 is a positive 21x, so that's going to be negative 21x because I went ahead and combined these two terms as well. Minus 4 plus 18x squared all over. Okay, finish cleaning this up. Z prime equals, I got a 9x squared, negative 9 plus 18 is 9x squared, minus 3 minus 21 is minus 24x, minus 4 all over 3x squared plus x quantity squared. There we go. All right, example 8. We want to find the derivative now. What rule are we going to use? Quotient rule. But before we find the derivative, wouldn't it be helpful if we rewrote this as u equals 5x plus 1 over 2x to the 1/2. So we're going to use the quotient rule. So using the quotient rule, we get u prime equals low d high minus high d low x to the negative 1/2 low d high minus high d low all over the denominator squared. So that's going to be 4x. Clean this up. Out of these two terms, I have a common factor of x to the negative 1/2. Now, if you took pre-cal, you got to practice quite a bit of this, where you pull out your common factors I have an x to the negative 1/2 in common here. And when I factor an x to the negative 1/2 out here, I end up with 10x minus 5x plus 1 all over 4x. Now, if you don't see what I did, I need to clarify and explain it. Do you see what I did or not? This is kind of different. Okay. I'm going to do a parallel problem here to kind of help it make sense. If you had 3x to the 4th plus 2x to the 1st, and I asked you to pull out your common, let's do 2x to the 2nd, and I asked you to pull out your common factor, your greatest common factor, what would it be? Well, and you decided that because that's the smallest power of x, right? Over here, what was our smallest power of x between this term and this term? X to the negative 1/2. I factored out my smallest power of x. So then when you write down what's left over, this is going to be 3x to the 2nd plus 2. Well, how did you get that 2 right there? You said 4 minus 2 is 2. Well, here I said, do you agree that the smallest power of x is x to the negative 1/2? Because negative 1/2 is smaller than 1/2, isn't it? And how you got this x to the 1st is 1/2 minus a negative 1/2. When you subtract a negative, you add. So 1/2 and 1/2 is 1. The 10 was just 2 times 5. And then this is the 5x plus 1. Oops, but it does need parentheses, doesn't it? Because I haven't distributed that negative yet. You with me? If it's complicated with the negative exponents and fractions and stuff, work a similar problem that has nice integer exponents. I did. The 5x plus 1, there's that term. It's multiplied, right? That's like the 2 right here, and there's my variable. And when I pulled it out, I'm left with just the 2. Negative 1, what I looked at when I looked at these two was the smallest power of x. So when I look at these two, I'm looking at the smallest power on x. Negative 1/2 is smaller than 1/2. So that's why that's what I pulled out was the negative 1/2. X to the negative 1/2. No, because there's no other common factor here. This is an expression that's in parentheses. You treat it as if it were a single entity. That's why I said, well, that's kind of like acting like your 2 did over here. Algebra. Algebra is the toughest part of calculus. The calculus rules are easy. I've got corny things to help you remember those. It's the algebra that will kick your tail in calculus. But I don't mind reviewing the algebra. Okay, because it's going to make my job easier in Cal 2. All right, u prime is equal to, now I'm going to distribute the negative, and can I just do it in my head right here and combine the like terms? 10x minus 5x is 5x minus 1 over 4x to the 3/2, because I'm going to take this term and move it down into the denominator. And then I have common bases, so rule says if you multiply with common bases, you add the exponent. There's an assumed exponent of 1 right here, so 1 plus 1/2 is 3/2. And now this looks nice, and we're done. Yeah, that's just this rule that we had here with the negative exponents. When you have a negative exponent, make it positive by moving it to the denominator. So what I did was I took that x to the negative 1/2 and I moved it to the denominator, and then we have another rule that says if you multiply with common bases, then you add the exponents, m plus n. So what I did was, this is x to the 1/2 times x to the 1st, so that's x to the 3/2.
Why did it turn from the negative 1/2 to positive?
Because I went from the numerator to the denominator. That's that negative exponent rule. If you have a to the negative n, that's 1 over positive a to the n. All these little rules that you didn't think were important when you first started learning them, There's a lot of them. And if you forget one, don't be afraid to just say, wait, how did you do that? I'll remind you of all these power rules. Okay? Not during a test, maybe, but in class and on your homework and stuff, definitely. All right. We have 7 more minutes and 2 more examples. I guess we're not going to get to these last 2 examples. By the way, quickly on number 9, get rid of that negative exponent. You want to rewrite this as w equals x plus 5 over 2x minus 7. Then it's an easy derivative. Okay? Right here, it's a product rule within a quotient rule, but you'll have the opportunity to ask homework questions. So we're done today.
Do you need the product rule first?